The second section of this chapter is limit of a sequence. So the definition of limit of a sequence. Let Sn be a sequence of real numbers then we say that Sn has limit L. The sequence Sn has limit L as n tends to infinity if for every epsilon greater than 0 there exists a positive integer, there exists a positive integer n such that the modulus of Sn minus L is less than epsilon, and it should be true for all n, natural number n greater or equal the large n. So we say this as equation star. That means it can be written as limit of Sn as n tends to infinity is L, or Sn tends to L as n tends to infinity, right? So it is similar to the definition of limit, but the sequence Sn has limit L if the difference is less than epsilon for all large numbers n, for all n greater or equal the large n. Right. So the note to show that means what we should do to show that the sequence Sn of real numbers has limit L. That means to show the limit of sequence Sn is L, it means we have to show that for every epsilon greater than 0 there must exist a natural number or positive integer n such that the difference is less than epsilon for all n, such that the difference of Sn and L is less than epsilon for all natural number n greater or equal the large n. That is, we have to find such positive integer n, such that the equation star, it should hold, the difference should be less than epsilon for all the natural numbers n greater than n, such that the equation star must hold. Right. So let us see some examples. For example, example 1. So consider the sequence. Consider the sequence 1, 1/2, 1/3, 1/4 and so on. So let the sequence is 1/n for all natural numbers or positive integer n. And as we know, the limit of this sequence is 0. So this sequence has limit 0. Right? So how to show this? To show this, How to show this? For given epsilon greater than 0, we must find a positive integer n. We must find a positive integer n such that the equation star should hold. That means Sn minus 0 should be less than epsilon for all n greater equal n. It must hold. Right? So now we consider the difference. Greater than 0. Consider this Sn minus 0, which is 1 by n minus 0, and what I want, it is 1 by n. What I want, we want this quantity to be less than epsilon for all n greater equal n. So we have to find the value of n for which the statement is true, right? So that is 1 upon n should be less than epsilon for all n greater equal n. That is, it means n should be greater than 1 upon epsilon from this, and it should be true for all n greater equal n. It means what? This will hold if this will hold. That means this will hold if this will hold. So it will be true for all n greater than 1 upon epsilon. So what large n I should choose so that it will hold? Right? So thus if we choose the large n to be greater than 1 upon epsilon, then definitely this difference will be less than epsilon for all n greater equal this capital N. And what is this capital N? It has to be greater than 1 upon epsilon. And we can say that limit of Sn as n tends to infinity is equal to 0. Right? So we have to choose the value of large n, and which is to be greater than 1 upon epsilon. So second example, so take it as an homework, that the sequence Sn equal to 1, that means it is a constant sequence for all n positive integers n. So what the limit would be? Has limit 1. So try to show. So for what value of large n the equation star holds? Right. So next example, number 3. The sequence Sn equal to n for all positive integers n does not have a limit. Does not have a limit. So how to show? It does not have a limit. That means there does not exist positive integer n that satisfy the equation star. Right? So to show this, suppose the given sequence Sn equal to n has limit L. So on contrary, we suppose the sequence has limit. What we wish to show? The sequence does not have a limit. So on contrary, suppose the given sequence has limit L. Right? So if the sequence has limit L, so the definition of limit of the sequence or the equation star will be satisfied by this sequence, right? So then for every epsilon greater than 0, there must exist a positive integer n such that the equation star is satisfied. That means Sn minus L is less than epsilon for all n greater equal n. So let us choose for epsilon equal to 1. We can have, so if I choose epsilon to be 1, so we can have Sn minus L to be equal to Sn is n minus L is less than 1, and it is true for all n greater equal n. So what does it mean? So by using the property of modulus, it will be minus 1 less than n minus L less than 1 for all n greater equal. And what does it mean? It means L minus 1 is less than n is less than L plus 1. True for all n greater equal 1. But what this statement says, statement or equation or inequality says. So this inequality shows that, what this inequality shows? So n lies between L minus 1 and L plus 1. So is it true the large n will lie between L minus 1 and L plus 1? Does it true? It shows that the values of n greater than capital N, values of n greater than capital N lies in between L minus 1 to L plus 1. So definitely not, right? So it is impossible. Because then limit would not be a definite or exist. So it is contrary to our assumption. So the given sequence Sn equal to n should not have any limit, right? Does not have any limit as n tends to infinity, right? Next example. Let me give it as a homework to you. Show that the sequence Sn equal to minus 1 raised to n for all positive integer n has no limit. Try to prove yourself. Then the next one is example 5. So find limit of sequence. Sn equal to 2n upon n plus 4 into n raised to half. N varies from 1 to infinity. So the solution. So let us consider the sequence Sn to be 2n upon n plus 4 into n raised to half. Okay. So let me find the value of this nth term, limit of this nth term, limit of Sn as n tends to infinity. So what it can be? 2n upon n plus 4 into n raised to half. So this limit can be evaluated by dividing by n to the numerator and the denominator. So at the numerator I will have 2, and in the denominator I will have it as 1 plus 4 upon n raised to half. And as n tends to infinity, so n raised to half, so definitely it will be 0, tends to 0. So the limit will be 2. So according to the definition of limit of sequence, how to show this? To show limit of Sn as n tends to infinity is 2. It is enough to show that for every epsilon greater than 0, we have to find a positive integer n such that the equation star should hold. Sn minus L is less than epsilon, and it is true for all n greater or equal n. This is equation star. So now consider difference 2n upon n plus 4 times n raised to half minus 2 is less than epsilon. So for what value of n this quantity is to be less than epsilon? So it means what? By simplifying this, it is 2n minus 2n will get cancelled. So it will be minus 8 times n raised to half upon n plus 4 times n raised to half. So the absolute value will be 8 times n raised to half on n plus 4 times n raised to half should be less than epsilon. So try to simplify this as it is. Now since this 8 into n raised to half upon n plus 4 into n raised to half, the quantity will be definitely less than 8 times n raised to half upon n. And then it is equal to 8 upon n raised to half. Right. So as this thing is, therefore 8 upon n raised to half is less than epsilon. It required this quantity to be less than epsilon. So that means what value of n to be chosen? That is, n should be greater than n raised to half should be greater than 8 upon epsilon. So the squaring both sides, n should be greater than 64 upon epsilon square. Therefore, thus if we choose a natural positive integer n or large n to be greater than 64 upon epsilon square, then our equation star must holds. That is, limit of, we can say that limit of Sn as n tends to infinity is 2, right? Then the next example. Okay, we skip the example and let us move to the theorem. The theorem. The statement is, if sequence Sn is a sequence of non-negative numbers and limit of Sn is L as n tends to infinity, then the limit will be greater than or equal to 0. Definitely it is true. It is sequence of non-negative numbers, that means positive numbers and 0. Then the limit of the sequence can be either 0 or greater than 0. So the proof, suppose what happens if the limit is not greater or equal 0? That means we suppose on contrary the limit is negative. Then what will happen? Then for epsilon equal to, epsilon is positive and L is negative. So if I consider L by 2, so it will be negative. So I consider minus of L by 2, which is to be positive. And since limit of Sn as n tends to infinity is L, therefore by definition of limit of sequence for every epsilon which is we have chosen to be minus L by 2 and is greater than 0, there exists a positive integer n such that equation star holds. That means Sn minus its limit is less than epsilon for all n greater or equal n. Right? The limit exists and it is L, which is we have considered it is to be negative. So that is Sn minus L is less than epsilon. Epsilon is what we have chosen it to be minus L by 2. So that is in particular it is true for all n greater equal large n. So in particular we consider for equal to the large n, Sn minus L is less than minus L by 2. Right? That means it will be minus of minus L by 2. That means L by 2 less than Sn minus L is less than minus of L by 2. So what do we get? That is, it means from these two terms Sn will be less than minus L by 2 plus L. So it is less than L by 2. So if the limit of the sequence is L, so is it true that for large n the sequence will be less than L by 2? Definitely not. And it is sequence of non-negative real numbers. So it says that the nth term is less than L by 2. That means negative? No, definitely not. Since L is less than 0, L by 2 is less than 0 implies the nth term of the sequence is negative and is a contradiction. To the sequence Sn is a sequence of non-negative numbers. So L cannot be negative. So L has to be positive or greater than 0. Right? So let us see example. If Sn is a sequence of real numbers if Sn is less equal capital M when n is a positive integer and limit of Sn is L, then this L is also less equal capital M. Okay. So the solution, what we have given Sn is sequence of real numbers. It is bounded by some real number M. Then if limit of sequence is L, then definitely this limit is less equal the upper bound of the sequence. Right? So it is given that sequence Sn is bounded by M for all positive integer n. So that means the sequence M minus Sn is positive for all integers or positive integers n. So it means what? So that means it is M minus Sn is also a sequence of non-negative numbers. Sequence of non-negative numbers. Therefore, by previous theorem, the limit of the sequence M minus Sn should be greater equal 0. That means L has to be greater equal 0. Right? That means that is M minus limit of Sn as n tends to infinity has to be greater equal 0. That is M minus L. It is the limit is L. It is given is greater equal 0 or L is less equal M, and it is what we wish to show. The next example, number 2, it is find a positive integer n such that the absolute value of 2n upon n plus 3 minus 2, it should be less than 1 by 5, and it should be true for all n greater equal n. Right? So solution, we have to find the largest value of n satisfying this. We have to find value of large n so that the least value of n satisfy this thing. Right? So solution, consider it should hold 2n upon n plus 3 minus 2 is less than 1 by 5 for a natural number or positive integer n. So simplify this thing. It means it is 2n minus 6 divided by n plus 3 less than 1 by 5, and n is positive integer. So it means by simplifying and taking absolute value, it is 6 upon n plus 3 less than 1 by 5 when n is positive integer. Or then now simplify this thing. 30 is less than n plus 3 when n is positive integer. So n should be greater than 27. So this thing will satisfy if n is greater than 27. Right? So what the large value of large n or smallest value of n or value of large n satisfying this thing or this equation, this inequality or the equation star will be greater than 27. Therefore, so if we choose a value of large n or least value of small n satisfying this equation, so if we choose large n such that it should be greater than 27, then our equation 1 must hold. So the value of capital N satisfying this is at least 28. That means greater than 27.